Yeah, I could also entitle this speech over here My Adventures with Hans Herrmann. And we'll zip through 2 decades, I guess, or even more. 3. Because it all started in Stuttgart, where I did my PhD, my habilitation, and we ran together a workshop on traffic and granular flow. And here's some pictures taken at that time, not exactly at that workshop, so I'm cheating a little bit over here, but you get an impression of how we used to look like 30 years ago. And already at that time, Hans was very much engaged, giving speeches and so on. And he was, of course, working on granular materials. And for example, he was interested in this size segregation that happens if you have a system with differently sized particles and share the system. And the approach that Hans has taken at the time was very much based on molecular dynamics. And this is me at that time. You see, also a little bit engaged. And I was applying the same thing to traffic and pedestrians, and that happened to be my thesis. Hans was actually one of the reviewers and was very much scared of him, because he had so many critical questions. He was so super smart, and I always wanted to be like him. So he published at least 1 paper a week. I had the impression, maybe I'm exaggerating a little bit, but he was just amazingly productive and all over the place. That means all over the world. And I was trying to be as good as he was, and he was very much inspired for me, and it was a very good force in my career. And talking about forces, of course, I've been working on the social force model for pedestrians. And so we were, of course, inspired by physics, and the idea was that we could understand the walking behavior of people through force equations, an equation of motion for pedestrian alpha. That means location changes would be given by the speed. Okay, that's kind of sure, but then the question was how to specify the acceleration. And we decided to formulate it as a superposition of different kind of forces that would describe different effects on people's behavior. For example, the effect of interaction with other pedestrians beta, or the interaction with boundaries. We assume repulsive effects, and we also assume that people, as compared to particles, would have goals, destinations, and they wanted to get into a certain direction of motion, E alpha naught, and they would have a certain desired speed, V alpha naught, and it would take some time to adjust the actual speed to the desired speed, and so on. So in the beginning, these were assumptions, and we did simulations later on. In fact, we even did experiments, and we analyzed trajectories, and it turns out that a lot of the assumptions that we made at that time are still being used and have been confirmed empirically and experimentally. Of course, in the meantime, there's some evolution of the modeling effort, but anyway, there's still a lot of people who are fascinated by self-organization phenomena in pedestrian crowds, and similar to the size segregation, you find over here a separation of the different walking directions into lanes. And in fact, that paper was published around 1995. There were several papers looking at different kinds of things, but this actually became one of the milestone papers of PRE. It collected quite a few citations, in fact, even though it seems to be such an unusual subject in physics. We also found some other phenomena, such as oscillations, bottlenecks, again self-organized, as you can see over here, and we like that very much, and we'll see that we learned from this actually that we can build self-organized traffic light control that would use this pressure principle that caused self-organized oscillations to come up with a very efficient traffic light control that works in a decentralized way and is actually implemented in Dresden and soon in Lucerne, maybe also Zurich and other places. So Stefan Lemmer is really the key person. He was a PhD in my team at that time. And yes, but lane formation oscillation is not the only thing that we discover. There's also stride formation phenomena. That means if there are two crossing flows of people, then it's possible that people cross the other stream without even stopping, right? So they would move forward with such a stride, but sideways within the stripe, and in such a way it's really possible to cross a flow without stopping. It's amazing, right? If you had to figure it out, it would take a long time, I guess. But we just do it automatically based on interactions. Another subject that I was interested in at the time in Stuttgart was traffic flow. And eventually it was a review of modern physics article. Actually, this was summarizing everything I've learned in the Stuttgart Times, and also a popular article. What we found was a surprising richness of different congestion patterns, and we decided that we should try to decompose complex congestion patterns into elementary patterns, as physicists basically try to understand properties of matter based on properties of elementary particles. And so we actually managed not only to simulate these elementary patterns, we actually did that before we had the data, so that was kind of predictive. And also we compared that later on with empirical data. So you can do that kind of simulation with different kind of models, for example, microscopic models, such as the intelligent driver model, and again you have an equation of motion, an acceleration equation, and a car following aspect. And then you can predict what will happen under certain kind of flow conditions. If you have a freeway with an on-ramp where there's some incoming vehicles, so basically you have the upstream flow on the freeway, the inflow through the ramp. The sum of both is basically the overall traffic volume. So as we go up here, we'll get into areas of high traffic volume, and from free traffic flow to congested traffic. And those different kinds of congestion patterns, you can see there's multi-stability. It all depends on how big is the perturbation, not only how big are the two flows, but there is a prediction of what will happen under what kind of conditions, and then eventually we did this hard work to gather data sets and to evaluate the data sets, and actually it turns out to fit the theory very well. And that also was published in Science. And there is now an analytical theory of traffic flow, a collection of 8 papers, I believe, and we can say that even though traffic flows are complex systems, we can understand the main features analytically, and we have theories that allow us to predict extensions and delays by traffic jams, and I think this is really a nice achievement. But we didn't leave it there. We also started to think about ways to get rid of those traffic jams. So we were assuming that cars would get smarter and smarter. Was still at times when nobody was talking about Google self-driving cars. We assumed cars would have onboard data acquisition, something like perception. Inter-vehicle communication was tested already at that time. We assumed that there would be cognition, maybe based on putting data of several vehicles together. It means a collective cognition, then decision making, and driver assistant or automatic driving. And we tested that even on roads at that time. So it was not just a computer simulation such as this one. And here you first get a demonstration of our understanding of stop-and-go traffic, which unfortunately happens still every day because our freeways are not very well organized. And we'll see in a minute what is the reason for this terrible congestion. We'll leave the car, we'll take the helicopter now, and we can see now that there is an on-ramp, there are some vehicles that are trying to get on the freeway, which produces small disruptions in the traffic flow on the freeway, and those disruptions are being amplified, and that causes some stop-and-go traffic. Now, without changing the inflows, we'll change the interactions between the vehicles now. We add some radar sensors that measure distances and relative velocities, and let the cars accelerate and decelerate automatically according to a certain formula. And even if we only equip 30% of those vehicles, we would be able to dissolve the traffic jams. How do we do this? Basically, by real-time measurement and real-time feedback. So we're changing the interactions between the vehicles in such a way that self-organization would lead to a favorable outcome, namely free traffic flow. And then eventually I got a chair of sociology at ETH Zurich. Maybe you know this chair that was standing in front of the hotel Zurichberg. So I had to grow into this, you know. And so we went big. And the first thing we did is we established this competence center coping with crisis in complex socioeconomic systems. Hans was part of it. And here are the others. So we were 6 people all together. We successfully raised some money, and we were all extremely ambitious, and everyone was publishing papers like hell, and everyone wanted to publish more papers than the others. And here are all the people, and here are the PhDs, postdocs included, who of course did a lot of the work with us, and it was a lot of fun, and we learned a lot. And then eventually this competence center was closed down to give place to an even bigger competence center, the risk center, and Hans Gersbach, for example, was also part of it, and many other people that you know of. So here you can see all the faces, and then we were interested in complex interdependencies in complex systems, so we realized that networking is good, but can promote cascading effects. And next week we'll have again a meeting of the World Economic Forum. They always publish these risk maps, and you can see that basically every system is somehow stronger or weaker connected to every other system, so they can occur all sorts of cascading effects, and things are getting more and more serious the more connected the world gets. So here's just an analysis of what may happen in case of an earthquake. We analyzed reports of many earthquakes and what happened in the aftermath, and you can identify a causality network, basically what leads to what, and you can take anticipated measures basically before the next bricks fall or the next dominoes fall. You can be there and try to prevent it from happening. And here you see some common elements of many disasters, and worst comes to worst. One disaster may trigger another disaster. For example, an earthquake could cause a volcanic eruption, and could cause tsunamis and floods and all sorts of things, and gas pipes might break, and so on and so on and so on. So it's good to know this beforehand so you can prepare for these kind of events. And one of the problems that both Hans and I were interested in were electrical blackouts and power grids. And so if that happens, basically, yes, of course, the traffic lights will be off, gas stations will be out of order, public and private transport will be down, will be disruption of the cellular phone network, and pumps will be without power, so you have to boil water, and you have to do that basically with gas, and then there would be more fires, and firefighters would have to come and save you in case of such a situation. So things can get quite complicated and bad in a very short time. Of course, people like Hans and myself and many others have been working on cascading effects in electrical power grids. So if there's a local overload that could cause an overload elsewhere, and then really, as this simulation by another team shows, very astonishing dynamics can happen, where basically a blackout down there in Spain can actually trigger a blackout in Eastern Europe. You wouldn't really think that such a thing would happen, right? And those things do happen actually. It turned out that on November 4, 2006, a ship had to cross a certain point, and they had to turn off one power line, and that caused a cascading effect, even though they made some analysis before, but they didn't expect a combination of switching off this line and a random failure, and suddenly you had blackouts all over Europe down to Spain, even though it all started in Germany, right? Of course, Hans was there to save the world, and he came up with ways basically to change the network, the power grid in such a way that you could mitigate the situation, you could make these power grids much more robust. But that was not all. Eventually we decided we would go really big, and it was this flagship competition, and so with the Future ICT project we applied for this €1 billion project, and we came into the final round, as you know. We had really big plans. We wanted to create a planetary nervous system to measure what's going on in the world, and we wanted to create a living Earth simulator in order to look into possible futures and be able to choose favorable scenarios, and we wanted to create a global participatory platform that would allow everyone to benefit from that kind of technology. And the project was big, and so it had many different focus areas. It was also socially inspired ICT and global system science, and we wanted to build various exploratories for financial systems, health and epidemics, crime and conflict, risk and resilience, sustainable cities, smart energy systems, environmental sustainability. We wanted to create an innovation accelerator, and across everything there would be ethics and integration. You all know how it ended. We didn't quite make it. It was very close. The Human Brain Project got the funding, and the Graphene Project, that was the illustration that ETH was publishing at that time. And of course, we never give up, right? That's why we are scientists. And so the first thing that I did is I built the SWAT team, students working against time. And Lucas, who is sitting in this audience, was one of those student assistants who were helping really to push scientific progress ahead with their help. And nothing could scare him, as you can see. And one of the papers that was published at that time was this Nature Perspective, Globally Networked Risk and How to Respond. And so it said that today strongly connected global networks have produced highly independent systems that we do not understand and cannot control well. These systems are vulnerable to failure at all scales, posing serious threats to society even when external shocks are absent. As the complexity and interaction strengths in our network will increase, man-made systems can become unstable, creating uncontrollable situations even when decision makers are well skilled, have all data and technology at their disposal, and do their best. And to make this system manageable, we would basically have to redesign those systems. We were calling for global system science, and we were asking the question, have humans created something like a global time bomb? Involuntarily, of course, by connecting systems more and more, such that cascading effects were more and more likely and less controllable. And we are probably in a situation which pretty much is like this. If you look at this fake news epidemics, I think this is a result of overconnectivity, and of course, you know, all this beautiful work by Robotsev and others on the scaling laws and to the implications depending on the different scaling exponents. So under certain circumstances, there would not be even a mean value or a variance well defined. And so anything could happen in those systems, and as a result, we were looking into systems that would produce all sorts of surprises. For example, these kinds of cooperation problems, where people interact with their neighbors. As you will see in a second, blue means cooperative behavior, red means non-cooperative behavior, and black is not occupied. Oh, I have maybe accelerated. So in the beginning, you see there's a lot of defection, cooperation is lacking, but eventually, in particular, if we add a few links to the network, we'll see cooperation spread. So now there's quite a few blue sites, and eventually it's the majority of sites, right? And we go on connecting the system more and more, and it turns out that unfortunately cooperation gets lost. That means more connectivity is not necessarily a good thing. There is an optimal degree of connectivity, and so maybe we have over-connected the world and destroyed a lot of cooperation by this unintentionally. Similar thing in systems where you could have epidemic breakouts. So assume some people make air flights to other countries, and maybe they have the flu, and so they would infect other people. And you know, as long as there are little flights in the system, yeah, it stays okay. You know, there are some people who are infected, but most people are healthy, and nothing bad here. But eventually, you know, we would add those long-range connections, and people would dislocate themselves to other places. And if there are few connections, it's okay, but if there are a few connections too much, then it can end this way. So that was the kind of stuff that was really getting our interest at that time, and we published also this paper about disease-induced resource constraints that could trigger explosive epidemics. Unfortunately, at that time when we wanted to publish this, there was just this Ebola breakout, and everyone thought we had this Ebola thing in mind, and that was not actually the intention. But anyway, so it got published, and you can see that there are these kind of discontinuous transitions over here due to the hitting of the resource constraints. We've also been looking in other kind of systems which would produce power law behavior, but without thresholds built into the model. And for this, we have been looking at that multi-particle system, a one-dimensional one, where basically each particle would be fixed to a location with a spring, and they could collide with each other, and there could also be a random influence on the behavior. And if you simulate it, then you get basically this behavior over here. So this turns out to be a version of Newton's cradle, and you can see that those particles at the boundaries really have sometimes very big amplitudes, while the ones in the middle have small amplitudes. And this is exactly what our study was about. So we found those parallel behaviors, in particular if you go to bigger and bigger systems. And now Lucas was not busy enough with this, so we started to look into other kinds of problems, such as the Erasmus Mobility Program. That was basically a data science study, and he discovered that female students are overrepresented in the Erasmus program, systematic across subject areas and also across countries. So they're really adventurous, one should say. Now, eventually, even though we didn't get the money for the Future ICT project, we can say that a lot of things happened throughout Europe and elsewhere. Data science spread, computational social science was established as a fastly growing field. Global system science made its way, looking into all sorts of data, spreading of scientific innovation, spreading of memes, spreading of culture, epidemic spreading, and so on. And social physics also made its way and got kind of popular attention through the book of Sandy Pentland, even though he was neither a physicist nor a social scientist. His book got quite some attention. And then the Singapore ETH Center on Sustainable Development was established. You can see one of the figures that Dirk Brockman had produced in collaboration with me. And then even Frank Schweitzer started organizing computational social science symposia, and if you go to the homepage of ETH Search, you would probably find this thing over here, which also shows a picture that was created in collaboration of our team with Max Schich and that appeared in Science. So, you know, this has all been spreading all over the place. Now, of course, in the meantime, we're living in a time of big data. And in the beginning of those times, people like Sandy Pentland thought eventually you would have kind of God's eyes view, and we could know everything. And exploratories were built also, as far as I can tell. The planetary nervous system was built in a living Earth simulator, but unfortunately not available for the scientists like you and me or the general public. The amounts of data became so big that one needed to have new technologies to evaluate the data. Artificial intelligence made its way. People are expecting super intelligent systems too, and those systems are so good at learning and are using so much data also about each of us that they learned how to manipulate our opinions and decisions and behaviors, and even elections, as we learned in connection with Cambridge Analytica. So personalized information is guiding our thinking in a sense, and some people were even thinking of society like a giant machine that could now be controlled by a huge AI system to behave in certain kinds of ways. And eventually people got concerned. So, for example, this Enigma project by Sandy Pentland that was basically looking into a scenario which we will see flash up in a second. So in the background there was Bentham's Panopticon, kind of the perfect prison now digitally implemented, and of course that had to be changed, and there was a fierce discussion about the digital future that we would enter and how it would look like. And my argument was that even though we would have more processing power than ever and more data then in the entire history of humankind we would still lose control of this planet if we try to control it in a top-down way, because systemic complexity would increase factorially, even faster than exponential. And as a result, there was just not enough processing power and data, and one needed a new control paradigm, which is basically distributed control and self-organization. That brings us back to the things that we discussed before. It became clear that we would have to think about ethical ICT, decide for values, digital democracy, and all of this. And in fact, that was making me busy in the past years, and we published this Digital Manifest in Spektrum der Wissenschaft that made a splash and created quite a bit of political upheaval, I would say. And you can see it triggered off a lot of activities. For example, this Manifesto for Digital Democracy by the University of Zurich, and there was this Digital Manifesto of Bern, where a lot of high-ranking people, so-called digital shapers, were meeting. In the meantime, this is what you find on the internet. Hopefully that's not a bad omen for the digital future of Switzerland. But there were all these people, you know. You can see me in the background over here, and a lot of those digital shapers that are pushing things ahead in Switzerland. And that was basically the plan, Digital Switzerland, built on freedom and initiative of everyone. That means a decentralized concept, and hopefully we'll have that and enjoy that together very soon. There were also risk center workshops on digital society, and suddenly there were all sorts of initiatives on digital societies at Collegium Helveticum, and in Bern there's a Center for Digital Society, and at the UZETA there's this Digital Society initiative. So it really cascaded in a sense. And so basically there's a new paradigm to go away from top-down control to a culture of empowerment, go away from this over-regulation by very detailed laws, and instead an approach that would look for system designs that support self-organization. In this case, of course, it's this unidirectional flow that we have in front, and the unidirectional flow in the opposite direction that we have in the back, and this little buffer in the middle that allows everyone to adjust the speed in such a way that you would find a gap to cross. And this is working surprisingly well. Of course, we can do that better with technology, right? And so this self-organization principle that I showed you before, pedestrians with oscillated bottlenecks, that can be transferred actually to the self-organization of intersections in cities, and we've done this, and the success is tremendous. You can see a lot of savings of travel times, public transport, even improvement for motorized traffic, even though there were green waves before, and also improvement for pedestrian cyclists and for the environment. And so that brings us to one more paper that I've written with Hans. It was a fun paper, but actually not taken too seriously. We just like to explore what happens in certain kind of settings. In this case, we were basically combining opposite flows of pedestrians with the redshift dynamics. And it turns out that this is stabilizing the lanes. And then years later, unexpectedly, we got an email that said, you know, we have implemented it. So SBB, the Swiss train operation company, was inviting us. And you can see we all tried out their virtual reality environment where they have been testing their solution beforehand, and it's there. It really exists. So you see it in the background. It looks a little bit different from how we had simulated things, but anyway, it was really funny to see how people were inspired by a paper. Usually people in a business would probably not read, and see, little by little, your publications can change the world. Now, one of the most exciting travels I've done was actually to Brazil. Hans invited me over, and so I was to talk about the next civilization. I was in a public theater in Fortaleza. You can see really a big event. I think the first event in a series of events that were to come up, and I talked about data and digital revolution and all this, and a short time later I think a few millions were actually spent on new research in data infrastructures. Finishing up with how this trip actually continued. So we were going to Rio de Janeiro, and we were meeting the people from SwissNext who were kind enough to organize this event, and then eventually we were also visiting this statue of Christ. And that allows me to close the circle, because that was about the time where people were saying, these super intelligent systems, they would be like an AI god that knows everything better than a human would know, and it would tell us how to live. And if we wouldn't live as that AI god would tell us, we would get minus points in the citizen score, which is currently tested, as you know, in China in some places. So we were in a situation where some people from Google and elsewhere were starting to believe, yes, we are all part of a huge network of people. We are now all one organism in a sense, and the only thing that's needed to coordinate those different cells of the organism that we would be kind of a super brain to control that super organism. And I said, not sure this is the way we want to live. And so, dear Hans, I'd like to dedicate these two books to you. Actually, do you know these people? This is Vincent Cerf, father of the internet. This is nearly